Cable stayed bridge is very similar to the cable suspension bridge, where the cables supporting the deck are suspended vertically from the main suspension cable, which are running between the towers and anchored at both ends of the bridge. In cable-stayed bridge, the cables extend from the tower directly connecting to the deck. The cables come to a dead-end anchorage at the deck and either individually anchored at the tower or it will pass through a saddle at the tower, then to the deck at an other end. The self-weight of the superstructure and traffic load on it primarily transferred by the stay cables, which are in tension. Stay cables transfers the loads to the tower through a saddle or individually anchored. The saddle allows the cable to change the force direction and distribute the tensile force onto the tower as compressive force. In the same way, in individually anchored stay cables, if you visualize the components of cable force in two dimensions, the components in x-axis will cancel each other out, resulting in a net force of 0 at x-axis. The components in y-axis will act as compressive force to the towers. This is how the gigantic towers experience compressive forces and transmit these loads to the huge and capable foundations and finally to the ground. Let's understand the components in detail. The anchorage system is very crucial for transferring the loads from the deck slab to the cables. This is the anchorage, which is designed to securely hold the high-tension cables in place by the conical wedges, using a combination of friction and compressive force. Then distribute this concentrated high tensile force over a wider area called as bearing plate. Bearing plate primarily acts as an intermediary component between the anchorage and concrete surface, which distributes the concentrated loads from the anchorage over a wider area of the concrete, preventing localized crushing or cracking due to the concentrated load. The stay cables are composed of multiple parallel strands bundled together. Each strand most commonly arranged in a 7-wire configuration with one central wire and 6 surrounding wires. These wires are high-strength, low-relaxation steel wires. The high-strength property comes from the high carbon steel used, allowing it to withstand very high tensile loads. While the low relaxation means it maintains its tension over the time without significant loss of stress. The number of strands inside each stay cable can vary significantly depending on the design requirements and can range from only few to more than 100. In modern cable-stayed bridges, the strands are protected by 3-layer corrosion protection system. The primary barrier is provided by a standard zinc galvanization of each wire for superior corrosion resistance, then wax as filler material to block the moisture and oxygen entry by sealing the gaps, and finally enclosed in high-density polyethylene sheathing, which acts as a protective barrier against mechanical damages like impact, abrasion, etc., and environmental damages like rain, UV, etc. But the HDPE sheathing should be removed for a specific length as mentioned in the drawing within the anchorage zone. The purpose is to allow the anchoring wedges to properly grip the steel strand. This is anchor cap primarily serves to protect the exposed pre-stressing strands and anchor head from corrosion and physical damages. The voids within the anchorage system are typically filled with grease or wax to protect from moisture and prevent corrosion. A stay cable is subjected to lateral movements as a result of vibrations. These vibrations increase the potential for fatigue. To address this issue, most cable-stayed bridges having damping devices, which are nothing but the neoprene rubber rings placed around the cables within the guide pipe. This device potentially reduces the vibration to an extent and improves the lifespan of the bridges. This is the saddle, which provides a curved surface for the cable to rest on the tower. A useful real-life analogy for the cable-stayed bridge saddle is the saddle used on a horse. A horse saddle is carved so the rider's weight is spread evenly, which prevents the pain or injury to the horse and keeps the rider stable and stops slipping. The cables carry huge forces, and this curvature is crucial for distributing the loads evenly and smoothly into the tower, instead of concentrating it at one point and preventing excessive stress on the cable or the tower. Generally, in conventional cable-stayed bridges, the cables are typically in two planes separated by the width of the roadway, providing balanced load transfer and minimizing torsional effect. But there are some recent modern bridges where you can see the cable stays in the central plane between the two opposing lanes of traffic, which requires the superstructure to be designed for torsional resistance. If you like this video, make sure you hit the subscribe button below and click on the bell to turn on the notification.